nuclear energy sources.
With Big Papa Levis, Little Boy Mikey, and the crazy Korean Kane.
This video will be giving you a brief description of fusion, fission, describing how the energy can be obtained from the atomic nucleus, concepts of mass defect, binding energy, and Einstein's famous equivalence equation.
Let's start off with a basic oxygen nucleus. In the nucleus there are 8 protons, 8 neutrons, making 16 nucleons. The total weight of an oxygen nucleus is 15.99 AMU, but 16 nucleons weighs 16.13 AMU, being an atomic mass unit.
Hey, but Mike, where did that mass go?
Well, Jack, this loss of mass has been coined mass defect. To explain this loss of mass, or mass defect, we're going to bring to light the most famous equation
in the world.
E equals mc squared. E equals mc squared.
Due to Albert Einstein's famous equation stating that mass is interchangeable with energy, this loss of mass is revealed through energy. This energy holds the nucleons together inside the nucleus. This energy is known as the binding energy, the energy required to bind the nucleons within the nucleus. This can be calculated using the equation E equals mc squared.
E equals mc squared. Energy in joules, mass in kilograms, speed of light in meter per second.
Using the equation on screen, we can find the binding energy of one nucleus of oxygen. Using this equation, we can find that the binding energy of one nucleus of oxygen is negative 2.04 times 10 to the negative 11th joules, the negative resembling that the energy is being given off. Now, while this might not seem like a lot of energy, this is only for one nucleus of one oxygen atom. Times this by 6.023 times 10 to the 23rd gets you the amount of binding energy in 1 mole of oxygen. Now, whilst this might only seem like a small number on your screen, to get this same amount of energy from coal, it would require the burning of 420 metric tons.
But Big Mike, how is this energy obtained from the nucleus?
Let's first start off with the 2 ways we can obtain energy from the nucleus. Fission, which is the splitting of a larger nucleus into 2 lighter ones, and fusion, which is the joining of 2 lighter nuclei to form a larger one.
Let's start off with fission. Fission is the way in which at present we obtain energy from the nucleus. This is done by bombarding a nucleus with neutrons, making the nucleus unstable, therefore causing it to break into 2 smaller nuclei with a similar mass. This break causes the release of the binding energy that was previously holding the nucleons together in the nucleus in the form of heat. This heat is then used to convert water into steam, sending steam through turbines, thus powering generators which emit power. Now, as previously shown, 1 oxygen mole can emit a fair amount of power, equal to that of burning 420 metric tons of coal. This is just the beginning. The most commonly used nuclear resource is uranium-235, due to bismuth stating that any isotope of an element with a mass number over 82 is considered unstable. Therefore, uranium-235, being an unstable isotope, will have a higher binding energy, as well due to the increased number of nucleons within the nucleus. This will result in a higher amount of heat energy given off during the reaction. This fission does require a large amount of power to initiate. However, scientist Otto Hahn has discovered that the resulting energy output is 200 million times the amount of energy of the nucleon that triggered it. This process is called fission. However, fusion is quite the opposite. This is the process of binding 2 smaller nuclei into that of a larger one. This process is much more efficient and releases an amount of energy that is colossal in comparison to that of fission, but it is extremely dangerous and near impossible to control. Looking at this blue graph, which shows the mass number of each element and the resultant power that would be emitted when obtaining nuclear energy from the nucleus. The power generated through fusion reactions would generate much more, as can be seen with the helium and hydrogen
down the bottom of the graph, showing a much higher resultant output of power. This power generated through fusion is easily viewable through the behaviour of our sun or a hydrogen bomb, which, as you can see, would not be the easiest thing in the world to control. It requires 10 million Kelvin, an insane speed or pull of force on the nuclei together, and this is why the roughly 27 million degrees Celsius sun, in combination with the sun's massive gravity, is enough to force the fusion reaction. Obviously, the gravity and temperature are fairly hard to emulate here on Earth, and that is why it is not a safe investment to initiate on Earth.